want to thank the University of Maryland for hosting this. This is actually where I did my PhD work almost a decade ago. It's good to be back in College Park. And I'll be talking about lunar rock physics. So in the next decade, we're probably going to see a quantum leap from sort of exploration, fundamental science, moving towards resource utilization on the moon, which is a huge deal. And what that means is going past understanding the first couple centimeters of the lunar regolith to down to hundreds of meters. And that means moving to different sensing modalities. There's a lot to learn from the way that we do geophysical imaging on the Earth to apply to resource prospecting on the moon. And in order to do that, we need to know more about the rock physics of the lunar regolith. So I'm going to start with a little bit of motivation. I'm relatively new to planetary science, so there's probably people in here who are more familiar with this than I am, but I'm sure there's students in the room that'll appreciate this too. So a long time ago, during the Apollo missions, they were noticing that there was an extremely interesting seismic signal, which was that there seemed to be very low seismic absorption in the lunar regolith. So here are some seismograms of some impact experiments, and you can see that the seismograms ring out for tens of minutes. Basically, this pile of rocks was ringing like a bell. And as a comparison is an impact test from White Sands, New Mexico, where, you know, relatively similar energy densities, but the signal basically dies out in a matter of seconds. So why is this extremely different behavior? If you go on to process this, you get a value, seismic Q, the quality factor, that expresses the acoustic attenuation in the material, that is as high as 3,600. Just to give you a general idea, Earth materials, the quality factor of, you know, a sand or a sediment is on the order of 10 or 15. The mantle of the Earth is 650. So why is the regolith 4,000? So people turned to rock physics, and they went and they did some resonance experiments, and they found that if you bake off your experiments in high vacuum and you remove every single trace of volatiles, then you can recover the sort of high Qs that are observed on the actual moon. And going on to study the effects of small amounts of absorbed volatiles on the mechanical properties, they found that you also have a change in the adhesion of the particles, and at very low normal stresses, such as in microgravity or just on the surface of the Earth. In fact, the stiffness and thus the elastic velocities in materials are proportional to this sort of adhesion that's fundamentally controlled by the adsorption or the lack of adsorbed materials. So one of the questions that motivated the work that we're doing right now is, can we use this strong dependence of the acoustic properties on water in your system as a tool for exploration? You know, the original observations were trying to understand, you know, why is everything so dry? But now we're trying to find the places where maybe it's slightly wet or very wet. And so as a first pass, we've been doing some ultrasonic velocity measurements. So we use piezoelectric transducers on two sides of a sample, put it in a freezer, and then we measure wave velocities as the acoustic pulse travels through the material. We've done this on both saturated, slightly wet, meaning equilibrated with atmospheric water, probably poly-adsorbed layers of water on it, and then oven dried, which means not totally baked off, so, you know, maybe monolayer adsorbed materials. And we measure this as a function of temperature. So you can see that the blue data is a saturated sample. This is working with a lunar regolith analog material. And you can see most of the action happens right around zero. You go from a unfrozen, relatively slow velocity to a frozen, relatively high velocity. If you look at the wet sample, this is the one that's equilibrated with sort of atmospheric water, 30% relative humidity. You get this interesting behavior that is similar to what you see actually for freezing in microporous soils, which is a freezing point depression effect. And that's because the adsorbed waters has slightly different properties than bulk water does, and it's harder to get it to freeze. And so when you have it strongly adsorbed, then you end up with this extended region of partially molten water at the grain boundaries that somewhere around -30 maybe seems to level off. We need to do these measurements to much colder temperatures, obviously. But this shows you sort of the kind of behavior that we're looking at. And if you look at the dry sample, so that's a mono-adsorbed layer, you see relatively little temperature dependence, but the other plot I have are the velocities normalized by their totally frozen velocity. And in fact, you do see some temperature dependence, even to the monolayer material. The difference is less than 1%, but it is measurable. And it showcases a further degree of freezing point depression than the polylayer adsorbed material. So that's sort of an interesting physics observation. The other plot is maybe something that's operationally useful if you're trying to determine the amount, the abundance of water using a seismic survey on the moon. So using these values, the totally frozen values that we measure, you can, using a rock physics model, construct a relationship between the ice fraction, the volume of ice in the pore space, versus the elastic moduli. And the different colors here are a bunch of different rock physics models. And rock physics models are just a way to describe essentially complex materials that have multiple phases in them. And the details of them depend very much on the specific geometry of what you're looking at. So I plotted a bunch. These are not a complete list, but these are very common rock physics models that are used in geophysics here on the Earth. And if we pick one, the HS average, that's the Haaschen-Strickman average model, commonly used, it sort of falls in the middle of it. Then we can construct a relationship between your acoustic velocities, VP and VS, and ice fraction. So this is the kind of thing that would be used to interpret a seismic survey that was performed on the moon. But the specifics of this depend very much on which of those models it is that you choose. And which of the models is appropriate is not a known question, and in fact depends very much on the microstructure of the sample, which continues to be an open question. What does the ice look like in the regolith, and how do different possibilities, different configurations relate to the physical properties that we would use to measure in the samples? And so measuring microstructure is something we do at Berkeley Lab very much. I do a lot of work here at the Advanced Light Source, which is a synchrotron source, a source of X-rays. And we use it for all sorts of different things, but for this project, we've been performing microtomography. So microtomography allows you to make non-destructive 3D maps of the structure of your sample. So here is this regolith material that we're using. And as you can see, you can resolve the sort of brighter features there are crystallites that are in a glassy matrix. And the grayscale values here are actually quantitative, meaningful, the X-ray attenuation values that can potentially be mapped to the specific phases of the crystallites, although we haven't even got there. But because it's a non-destructive technique, it lets you to go inside your grains and also study the porosity that exists within the grains, which can be another place where trapped volatiles could be sitting. And you can understand the topology of that pore network, the transport properties, and you can understand the structure of the grain contacts, which is essential for this sort of study. So this is, we've done some of this initial quantification of this particular analog material, but there's a lot of work to be done. And more importantly, the title of this talk, we've been developing an X-ray transparent, ultra-high vacuum cryogenic vessel that will allow us to do imaging at real lunar surface conditions so that we can actually make a real appendix with real geometrical data about the topology of different textures of ice within the regolith. And the first version of this is going to have integrated acoustic sensors, so we can do the same kind of measurements that I was reporting from the benchtop there. So we'll be able to get down to ultra high vacuum and liquid nitrogen temps. We can control the axial stress to study the effects of overburden as you go down in the regolith. The initial version is going to have acoustic sensors, but we'll be able to extend to do dielectric measurements, electrical resistivity, and spectral induced polarity, which is another geophysical exploration tool that's commonly used. And yes, for all the spectroscopists, even potentially Raman. The applications, in addition to the lunar rock physics I was talking about, are non-destructive characterization of the returned materials, cryosphere applications, icy satellites, and something I'm really interested in, Martian hydrology. So yeah, I don't know if there's time for questions, but thanks.
Oh. Sorry, yeah, no time for questions. Very, very intriguing talk. Different approach to actually detecting water for ice. Are you?
Yeah, and I should mention actually the ALS is a user facility, which means anyone can write proposals to do experiments using this. So please get in touch.
Okay, thank you. Next talk, which is the third to the last talk in our session, is maybe second to last talk, is David Boswell, preparing spectroscopic tools for future space missions. Multimodal characterization, lunar and asteroid simulant samples using Raman spectral mapping, SCM, and FTIR analysis. I think that's the longest title as well. Thank you very much.